I want to tell you about the most beautiful lie in all of physics. And I've been telling this lie myself for decades. We say that light is both a wave and a particle. We tell students, well, sometimes it behaves like a wave, sometimes like a particle. We show them the double slit experiment and say, see, wave-particle duality! And you know what? That's complete nonsense. I don't mean it's wrong, exactly. I mean, it's not even a meaningful statement. It's like saying a photograph is both a tree and a piece of paper. You see, the question itself, is light a wave or a particle? That's the lie. And it took me years to understand why. Let me tell you what I discovered. Because once you see it, you can't unsee it. And it'll change everything you think you know about reality. When I was a young graduate student at MIT, this was 1939, I was barely 21 years old. I thought I understood quantum mechanics. I really did. I'd read Dirac's book cover to cover. I could solve the Schrödinger equation. I could calculate atomic spectra. I felt like I was getting it. But then John Wheeler, my advisor at Princeton, asked me a simple question. We were walking across campus, and he said, "Dick, what is an electron?" I said, "Well, it's a particle." He said, "Is it? What about wave functions? What about interference?" So I corrected myself. It's both a wave and a particle. And Wheeler stopped walking. He looked at me with this expression. I'll never forget it, like he was disappointed. And he said, "No, try again. You see, this was the standard story we all learned." In the early 1900s, physicists discovered that light, which everyone knew was a wave, Maxwell had proven it mathematically, you could see interference patterns, diffraction, all the wave phenomena. Light also came in discrete chunks. Einstein showed this with the photoelectric effect, individual photons knocking out individual electrons. Particle behavior. Then in the 1920s, de Broglie and Davison and Germer showed the opposite. Electrons, which everyone knew were particles, also made interference patterns like waves. Matter waves! The whole thing seemed completely contradictory. So Niels Bohr came up with this idea called complementarity. He said both descriptions are necessary. Wave and particle are complementary aspects of reality. You need both to have the complete picture. And for decades, that's what we taught. That's what I taught. But I couldn't accept it. Not deep down. Because it felt like a dodge, you know. It felt like we were saying, it's too complicated to understand, so let's just say it's both and move on. I remember late nights in my apartment in Princeton, 1941, 1942, working on problems, and I kept coming back to this question. What does it mean to say something is both a wave and a particle? Not mathematically. I could do the math. But physically, what's actually happening? And here's what bothered me most. When you measure where an electron is, you always find it in one place. Always. A point, a particle, you never measure it spread out like a wave. Never. But when you don't measure it, when you let it travel from one place to another, it acts like it goes through both slits in the double slit experiment. It interferes with itself. Wave behavior. So which is it when we're not looking? Is it, really, a wave that somehow becomes a particle when we measure it? That seemed mystical. Or is it, really, a particle that somehow knows about both paths? That seemed impossible. I spent years wrestling with this. And then I realized I was asking the wrong question entirely. Let me tell you where this started to crack open for me. It was 1946, just after the war. I was at Cornell trying to get back into physics after Los Alamos, and I was stuck, completely stuck. I'd spent 3 years building bombs, calculating neutron diffusion, all applied stuff. And now I wanted to do something beautiful, something fundamental. But I couldn't think. The war had, I don't know, it had done something to my brain. So I started playing. That's what saved me, actually. I stopped trying to solve big problems and just started playing with physics again. I remember sitting in the Cornell cafeteria, and some kid threw a plate in the air, and I noticed the plate was wobbling as it spun, and I thought, I wonder what the relationship is between the wobble rate and the spin rate. So I worked it out, just for fun, and it turned out to be really interesting mathematics. And that led me to think about electron spin, and that led me to relativistic equations, and within a few years, I developed a whole new way of doing quantum mechanics. But here's the thing, to develop this new approach, I had to completely rethink what was happening when a particle moved from one point to another. And that's when I started to see the lie. See, we'd always thought about quantum mechanics in terms of state vectors and wave functions. Schrödinger's approach. You write down a wave equation, and it tells you how the probability wave evolves in time. And we thought of this wave as a real thing, spreading out through space. But I asked myself, what if we think about it differently? What if, instead of a particle being a wave, we think about all the different ways a particle could get from point A to point B? Imagine an electron going from this point here to that point there. In classical physics, it takes one path, the path of least action, the path that minimizes energy. But what if, in quantum mechanics, it somehow explores every possible path? Now, that sounds crazy, and I thought it was crazy too. But then I remembered something Wheeler had told me about years earlier. There was this old idea from the 1930s by a physicist named Paul Dirac about summing over multiple paths. Wheeler had mentioned it once, casually, and I'd filed it away. So I started working with this idea, and what I discovered was beautiful. You could calculate everything in quantum mechanics, by imagining that the particle takes every possible path from start to finish, and you add up a contribution from each path. Each path contributes with a certain phase, a certain quantum mechanical angle, and when you add them all up, billions and billions of paths, infinite paths, most of them cancel out because their phases are different. But the paths that are close to the classical path, those reinforce each other. And that's where the particle is most likely to be found. You see what this means? The particle doesn't become a wave. The particle is always a particle, but the calculation of where it can go involves adding up these contributions from all possible paths, and that sum has wave-like properties. Each path contributes with a certain phase, a certain quantum mechanical angle, and when you add them all up, billions and billions of paths, infinite paths, most of them cancel out because their phases are different. But the paths that are close to the classical path, those reinforce each other. This was the beginning, but I didn't see the full picture yet, not by a long shot. In 1948, I presented this idea at a conference in the Pocono Mountains, and it did not go well. I stood up there with my diagrams, what people now call Feynman diagrams, and I tried to explain this path integral approach. And Niels Bohr just tore me apart. He stood up in the middle of my talk and said, "What about the uncertainty principle? What about complementarity? How can you talk about paths when we can't know both position and momentum?" And I tried to explain, I'm not saying we know the path. I'm saying we sum over all paths. It's a calculation tool. But he cut me off. He thought I was trying to bring back classical determinism, trying to sneak in hidden variables. And maybe I wasn't explaining it well enough. I was young, I was nervous, and Bohr was, well, he was Bohr. I went home from that conference feeling terrible. Like maybe I was wrong. Like maybe I didn't understand quantum mechanics after all. And I thought about giving up on the whole thing. But then something happened that changed my perspective completely. I was teaching undergraduate quantum mechanics at Cornell, and I got to the double slit experiment. You know the one? You shoot electrons one at a time at a screen with two slits, and even though each electron goes through individually, over time they build up an interference pattern, like they somehow know about both slits. And I was explaining the standard interpretation. The electron is a wave, it goes through both slits, it interferes with itself. And one of my students raised his hand and said, "Professor Feynman, if it's a wave going through both slits, why does it always land at just one point on the detector? Shouldn't a wave hit lots of places at once?" And I opened my mouth to give the standard answer about wave function collapse. But then I stopped, because I realized I didn't believe that answer. What I believed, what my mathematics told me, was something different, something simpler and more radical at the same time. I said to the student, "Let me show you another way to think about it. The electron is a particle, always. It goes through one slit, but we don't know which one. So in our calculation, we have to add up two possibilities: the amplitude for going through the left slit plus the amplitude for going through the right slit. When you add those two amplitudes, those two quantum mechanical arrows rotating in complex number space, that's where the interference comes from. Not from the electron interfering with itself, from two possibilities interfering with each other in the mathematics." The student looked confused. "But if it only goes through one slit, how does it know about the other slit? How does it know whether the other slit is open or closed?" And that's when I said something that I've been saying ever since. It doesn't. The electron doesn't know anything. Nature doesn't calculate. We calculate. And the calculation requires us to include every possibility we haven't ruled out. You see, this is where the lie starts to reveal itself. We say wave-particle duality because we're trying to explain the mathematics with a picture. But quantum mechanics isn't about pictures. It's about amplitudes, complex numbers, probability calculations. There's no duality. There's no mystical switching between wave and particle. There's just the way quantum mechanics works. And it doesn't fit into our classical categories. But I still wasn't fully there yet. I still hadn't completely let go of the picture making. And it took a conversation with one of the greatest minds of the century to push me over the edge. In 1951, I visited the Institute for Advanced Study to give a talk, and after my talk, Albert Einstein asked if he could speak with me privately. Einstein wanted to talk to me. I was 33 years old, and I was about to have a private conversation with the man who'd invented relativity. We walked across the grounds, just the two of us, and he said, "I've been thinking about your path integral approach. It's very clever. But tell me, do you believe the electron actually takes all those paths?" And I said, "No, of course not. It's a mathematical device, a way of calculating probabilities." He nodded. "Good. Because if you believed the paths were real, you'd be in trouble." Then he said something I've never forgotten. "The electron arrives at the screen. That is a fact. Everything else, waves, particles, paths, these are just our attempts to predict that fact." And I said, "But people do treat the wave function as a real thing. They talk about collapse, about measurement causing the wave to collapse to a particle." And Einstein waved his hand dismissively. Yes, the measurement problem. Everyone talks about it. But what does it mean the wave function collapses? Does something physically collapse? Or do we just update our knowledge? We walked in silence for a moment. Then he said, "Dick, let me tell you something. In 1905, when I said light comes in quanta, everyone thought I was saying light is made of particles, little bullets flying through space. But that's not what I meant. I meant the energy exchanges happen in discrete amounts. That's all. The wave or particle question. It's a false dichotomy. It's like asking whether money is a wave or a particle. Money isn't a physical object at all. It's an abstraction, a tool we use to quantify exchange. Maybe quantum mechanical properties are like that. Real consequences, but no concrete picture. This conversation haunted me for years. Because Einstein was putting his finger on something crucial. We were trying to force quantum mechanics into ontological categories. What is it really? When maybe those categories don't apply. By the time I got to Caltech in the 1960s, I developed a whole way of teaching quantum mechanics that tried to avoid the wave-particle language. I'd start with the double-slit experiment, but I'd present it as a mystery, not waves and particles, but behavior that doesn't fit our classical intuitions. I'd tell my students, look, you can do two things. You can try to build a mental picture, waves, particles, whatever, and you'll always end up confused. Or you can learn the rules of quantum mechanics and learn to calculate. And once you can calculate, once you can predict what nature will do, then you understand it as well as anybody. But they'd always push back. But Dr. Feynman, what's really happening? Is the electron really in two places at once? Does the wave function really collapse? And I'd say, I don't know. Nobody knows. And here's the thing, we don't have to know. We have a mathematical framework that works perfectly. Every prediction it makes is correct. Why do we need more than that? But I could see in their faces, they weren't satisfied, and honestly, neither was I, not completely. Because there's a difference between saying, we don't need to ask, and actually understanding why the question doesn't make sense. And I didn't fully understand that yet. That final piece came later, much later, and it came from the most unexpected place, thinking about what we mean by observation and measurement. Here's the thing that kept nagging at me. If an electron isn't a wave or a particle, if it's just this abstract quantum system, then why does it look like a particle when we measure it? Why do we always detect it at a definite position, with a definite energy, not spread out? The standard answer was, measurement collapses the wave function. But what's a measurement? Is it consciousness? Does my brain have some special physical property that collapses wave functions? That seemed ridiculous. Or is it the apparatus? Does a Geiger counter have some special quantum collapsing property? Then where do you draw the line? Is a rock a measurement device? What about a bacterium? In the 1970s, I started thinking about measurement as just another quantum interaction. Nothing special. When an electron interacts with a detector, what actually happens is entanglement. The electron's quantum state becomes correlated with the detector's quantum state. If the electron is in a superposition, if our calculation says we need to add up multiple possibilities, then after the interaction, the whole system is in a superposition, electron plus detector. But now the detector is a macroscopic object, billions of atoms, connected to the environment, photons bouncing off it, air molecules colliding with it. All of those connections spread the quantum correlation outward. And when you have enough connections, enough entanglement with the environment, something remarkable happens. The different possibilities stop interfering with each other. It's called decoherence, and it happens incredibly fast, in a fraction of a nanosecond for something as big as a detector. Once it happens, each possibility evolves independently. No more interference. No more quantum behavior at the macroscopic level. And that's why the detector registers a definite outcome, not because of some mystical collapse, but because the quantum correlations have spread into an environment so complex that we can't track them anymore. And when we can't track them, they behave like classical probabilities. Now, when I started talking about this in lectures, people would say, but Dr. Feynman, you're not answering the question. You're just explaining why we see a definite outcome. But what's really there? Is it really in multiple states until we look? And that's when it finally clicked for me. That's the lie. Right there in that question. What's really there assumes there's some classical picture, some definite, visualizable reality underlying the mathematics. But there isn't. Let me put it this way. When I calculate quantum mechanical probabilities, I use complex numbers. Amplitudes. These aren't just mathematical tricks. They're fundamentally different from regular probabilities. They can be negative. They can cancel out. They have phase. You can't picture an amplitude. It's not a physical thing you can point to. But the consequences of amplitudes are physical. The interference pattern is real. The energy levels are real. The measurement outcomes are real. So here's what I finally understood the question. Is it a wave or a particle? Is asking for a picture, a classical picture. But quantum mechanics isn't a description of what things are. It's a description of what things do, how they evolve, how they interact, what probabilities we calculate. And those probabilities involve interference, adding amplitudes, which gives wave-like results. But the objects interfering aren't physical waves. They're possibilities, alternatives, different ways the mathematics can contribute to the final answer. There's an old saying in quantum mechanics, shut up and calculate. For a long time, I thought that was defeatist, like we were giving up on understanding. But now I think it's actually profound, because the calculation is the understanding. The mathematics isn't pointing to some deeper reality that we're missing. The mathematics is the reality, as deep as it gets. And once I saw that, once I really truly accepted it, the whole wave-particle duality dissolved. It just went away. So let me tell you what I discovered, what changed everything. There is no wave-particle duality. There never was. What there is a mathematical structure, quantum mechanics, that predicts the outcomes of experiments with perfect accuracy. And this structure doesn't fit into our classical categories. It uses complex, valued amplitudes. It requires you to add up contributions from all possible alternatives. It produces interference when alternatives are indistinguishable, and it produces classical behavior when alternatives become distinguishable through environmental interaction. That's it. That's quantum mechanics. No mysticism, no consciousness, no wave function living in some abstract Hilbert space waiting to collapse. Just a set of rules for calculating what happens. Now, when I say just rules, I don't mean it's not profound. God, it's the most profound thing I've ever encountered. Because what it means is that reality at its deepest level doesn't match any picture we can visualize. We evolved to understand medium-sized objects moving at medium speeds, rocks, trees, antelopes. Our brains build pictures, visual, spatial, causal pictures, because that's useful for survival. But nature at the quantum level doesn't care about what's useful for us. It does what it does. And what it does is interference of alternatives. That's the core phenomenon. That's the thing that makes quantum mechanics quantum. When you can't tell which slit the electron went through, you add the amplitudes, left plus right, and they interfere. When you can tell which slit, when you put a detector there, when information about the path gets recorded anywhere in the universe, you add the probabilities left plus right, and they don't interfere. It's not that measuring makes it become a particle. It's not that not measuring makes it be a wave. It's that the mathematical structure has these two rules, add amplitudes or add probabilities, depending on whether alternatives are distinguishable. And here's the beautiful part, the part that took me decades to appreciate. This isn't a limitation of our knowledge. It's not that there's a real electron taking a real path and we just don't know which one. Bell's theorem proved that hidden variables don't work. No, the alternative paths aren't real in the classical sense, but they contribute to the calculation, and the calculation determines what happens. So in a strange way, the alternatives are real, not as paths taken, but as necessary elements of the mathematical structure. It's like asking whether the number pi is real. Not real, like a rock, but real in the sense that it's a necessary part of mathematics, and mathematics describes nature. Phi is as real as it needs to be. Same with quantum amplitudes. Same with superposition. Same with the whole framework. It's as real as it needs to be to predict what we'll observe. And we shouldn't demand more than that. The lie, the beautiful lie, was ever thinking we could do better, ever thinking we could reduce quantum mechanics to something intuitive, something that matched our pre-quantum pictures of reality. We can't. And once you stop trying, once you accept the mathematics on its own terms, it's not confusing anymore. It's just beautiful. You know, I spent 50 years thinking about quantum mechanics. 50 years. And the lesson I learned is the hardest lesson for a physicist. Sometimes you have to give up on the picture. We want reality to make sense the way our everyday world makes sense. We want electrons to be things moving along paths existing in definite places. But they're not. Or rather, they're not only that. They're something stranger. Something our language struggles to capture. I used to think that meant we didn't understand quantum mechanics. But now I think it means we understand it as deeply as humans can understand something. We have a complete mathematical framework. It makes perfect predictions. It's been tested billions of times. Never wrong. The only thing we're missing is a story, a narrative that makes it feel comfortable. But nature doesn't owe us comfort. Nature doesn't owe us visualization. Nature is what it is, and we're lucky we have mathematics powerful enough to describe it. And actually, once you let go of the need for pictures, once you just let the mathematics speak, there's a real freedom in that, a real beauty. I can calculate how an electron moves through a crystal. I can predict the color of light an atom emits. I can design the transistors in a computer chip, not because I picture tiny billiard balls or tiny waves, but because I can calculate with amplitudes, add them, square them, get probabilities, and those calculations work. Every single time. Isn't that the most beautiful thing? That nature is mathematical at its core. That reality obeys these elegant rules, even if we can't draw a picture of them. You know, when I teach young physicists now, I tell them, don't worry about what it is. Learn what it does. Learn to calculate. Learn to predict. And once you can do that, once you've spent enough time with the mathematics that it becomes second nature, you'll start to feel like you understand it. Not understand in the sense of having a picture, but understand in the sense of knowing how nature behaves. And that's the only kind of understanding there is. I think about Wheeler's question from all those years ago. What is an electron? And now my answer is, an electron is an element of a mathematical structure, a quantum field, something that, when we calculate its behavior using the rules of quantum mechanics, produces the phenomena we observe. That's not a dodge. That's not giving up. That's accepting reality for what it is, not what we wish it were. The universe is under no obligation to make sense to you. It's under no obligation to match your intuitions, your pictures, your inherited categories of thought. But here's the miracle: we can still understand it. With mathematics, with experiment, with this beautiful interplay of theory and observation that we call science. Wave or particle? Neither. Both. The question is wrong. What quantum mechanics teaches us is that reality is richer than our categories, deeper than our pictures, more beautiful than our analogies. And if we're humble enough to let go of our need for visualizable mechanisms, If we're brave enough to follow the mathematics wherever it leads, we get to see how nature really works. And it's magnificent. That's the biggest quantum lie, the lie that confused us in the first place. The lie that said reality must fit our expectations. It doesn't, and thank God for that, because a universe that matched our expectations would be a boring place. This universe, this quantum mechanical, interference producing, amplitude adding, probability generating strange and beautiful universe. This is a place worth exploring. And I'm grateful I got to spend my life trying to understand it.